Alrighty, in this video we are going to be talking about improper integrals. Back in AB, whenever we talked about the definition of the definite integral, we talked about how f had to be continuous on A to B. Now, in this course, we're going to talk about what happens whenever f is not continuous, and let's say that we have a discontinuity between my interval, or we have an infinite discontinuity where our function goes on forever and ever and ever, just like how here with 1 over x squared, notice how we have some tiny area right here that we can't really find the area of using AB techniques. So that's what we have improper integrals. The first one that we are going to be talking about is type 1, which is infinite integrals, essentially looking at 1 over x squared, where, once again, we have this area right here that we're trying to find. So let's pretend that I have the area from 1 to t, and that's going to give me 1 minus 1 over t. Now, what happens is that if I change my t value to be closer and 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 closer to, let's say, infinity, then I can rewrite my integral so that it is from 1 to infinity to be the same thing as the limit as t approaches infinity of 1 to t of 1 over x squared. So this is going to be our proper notation in terms of what happens as we get closer and closer and closer and closer to infinity here. So that's why we take the limit. Now, your notation for this lesson is going to be very important. Notice how we have limits right here. So we're going to have limits for each of our subs. If you don't give me limits in each of the subs, then you risk losing your limit point. A couple of remarks. Sometimes it might not go from 1 to infinity. It might go from negative infinity to 1 or something like that. If we have an answer, then it's called convergent. If we do not have an answer, then it is divergent and the limit does not exist. Now, hypothetically, if we have something, let's say, from negative infinity to infinity, then we can split the integral up so that we go from negative infinity to a, and then a to infinity, where a is going to be some value that we could easily split up. Remember that infinity is not a symbol, is a symbol, not a number. We can't evaluate an antiderivative of f at infinity or negative infinity. So that's why we use the variable t in this case to represent infinity. This is going to be a two-step process. We are going to evaluate the definite integral and simplify it, and then we are going to evaluate the limit, proving that it exists. So let's look at number 1 here, where I have the integral from 1 to infinity of 1 over x squared plus x. Now, if I were to show you what this looks like right here, I'm going to have discontinuity at 0 and at negative 1. But notice how my bounds are from 1 to infinity, so that's okay. And honestly, if I were to look at this and look at what the graph looks like of 1 over x squared plus x, that is going to look something like this right here. So from 1 all the way to infinity. So we're trying to find out this area right here. Notice how here, as I get closer and closer and closer and closer to infinity, then my area just becomes obsolete. It essentially becomes 0. So, once again, what we are going to do here is have a variable that represents infinity, in this case t. So I'm going to have the limit as t approaches infinity from 1 to t of 1 over x plus 1 dx. Notice how here that this requires partial fraction decomposition. So I'm going to go ahead and think about what this decomposition is by saying a over x plus b over x plus 1 is equal to 1 over x plus 1. I'm going to go ahead and shorthand this by thinking about my LCD. So for my first term, I need an x plus 1. For my second term, I need an x. And for my third term, I don't really need anything, so that's just going to be 1. If I let x to be -1, then I'm going to have negative b is equal to 1, which means that b is equal to -1. And then if I let x to be 0, then I'm going to have a is equal to 1. So now I could rewrite my limit in my integral to be the limit as t approaches infinity from the integral of 1 to t of 1 over x minus 1 over x plus 1 dx. Once again, we need that limit notation throughout, so I'm going to go ahead and take the antiderivative, but taking the antiderivative requires that limit notation. So I have the limit as t approaches infinity of ln of x minus ln of x plus 1 from 1 to t. Now, hypothetically, because my integral is going from 1 to t and it's positive, I don't really need the absolute value bars here. So in the next step, I'm going to go ahead and take that out. But I'm going to go ahead and use FTC and go have ln of t minus ln of t plus 1. That's my first part. Minus ln of 1 minus ln of 2. Now, of course, we know that ln of 1 is going to be 0. So I have the limit as t approaches infinity of this lovely thing right here. And honestly, I could say plus ln of 2. Okay, so if I plug in infinity here, I'm going to have infinity. And if I plug in infinity here, I'm also going to have infinity. So that is going to give me indeterminate form of infinity minus infinity. Now, of course, what we can do here is think about how I can simplify this into 1 ln, which is going to help us a little bit, because then I'm going to have ln of t over ln of t plus 1. And if I take the limit as t approaches infinity now, I can think about my degrees. Since this is a degree of 1 and this is a degree of 1, then I'm going to have ln of, oops, let me rewrite that correctly. Since this is a degree of 1 and this is a degree of 1, and this is going to tell me that as I approach infinity, this limit is going to approach 1, which means I'm going to have ln of 1 plus ln of 2, but we know that ln of 1 is going to be 0, so my final answer here is just going to be ln of 2. So my final answer, the integral from 1 to infinity of 1 over x squared plus x, is ln of 2. All right, so what I want you guys to do is 2, 3, 4, 5, and a summary based off of what we just did here, where we take the limit as t approaches infinity, 1 to t of 1 over root x dx. We're getting the same thing for 3, 4, and 5. And then you're going to see what happens between 2, 3, 4, and 5, given that it's in the form of 1 over x to the p power, where p is your exponent. Something special does come up, so it is going to be very important that you understand what happens there in preparation for Unit 2. And I think these are easy integrals for you to deal with. So I think you guys can do that on your own. And you guys can check the student notes for that. But what we are going to do here is look at some other problems like 6, 7, 8, 9. I'll do a couple, but I'm not going to do all of them. Let's go ahead and do something like number 8 here, where we have the integral from negative infinity to infinity of 1 over 1 plus x squared. Now that one's pretty fun here. Notice how I have negative infinity to infinity. So what I'm going to do is split this up so that I am going to go from negative infinity to 0, and then 0 to infinity. You might be thinking, why am I splitting it down at 0 and not like 1 or 2 or 3? And you'll figure out why in a couple of seconds. What I'm going to do here is, because since I have 2 integrals, I'm going to do improper integrals twice. One for that one, and then one for this one right here. Now, I'm going to have the limit as t approaches negative infinity. Then I'm going to have t to 0 of 1 over x, 1 over 1 plus x squared dx. The antiderivative of that is inverse tangent. And you'll see that my bounds are from t to 0, which is why I picked 0, because if I did inverse tangent of 0, that's going to be 0. So then I have inverse tangent of 0 minus inverse tangent of t. Now, if I'm approaching negative infinity here, you guys also need to understand what inverse tangent looks like in terms of a graph. Remember that inverse tangent looks like this right here, where I have asymptotes at pi over 2 and negative pi over 2. And since I'm approaching negative infinity, this tells me that I'm going to have 0 minus negative pi over 2, which gives me an answer of pi over 2 for my first integral. Now, looking at my second integral, I'm not going to be using the same variable here, just so it doesn't confuse us. Instead, I'm going to use, let's say, a as the variable now. So now I have the limit as a approaches infinity of 0 to a of 1 over 1 plus x squared dx. Okay, once again, we know that is going to be inverse tangent. And once again, notice how I'm carrying my limits throughout. So then I have inverse tangent of a minus inverse tangent of 0 as a approaches infinity. We know that here, inverse tangent of a as it approaches infinity will converge to pi over 2. And we know that inverse tangent of 0 is just going to be 0. So that's going to be my second integral. So my first integral was pi over 2. My second integral was pi over 2. If I add them up, then my final answer is just going to be pi. So this is going to be my final answer. Whenever I split it up. All right, let's do one more. I'm gonna do 9. Your A-B integration techniques will also come into play here, so don't forget about them, and also don't forget about your BC integration techniques that we've learned. So don't forget about partial fractions, and don't forget about integration by parts, because you will see them with improper integrals, even though we haven't really talked about them here in the video. For number 9 here, I'm going to go ahead and move the e to the x squared up top so that I have the limit as t approaches infinity of 1 to t of 2x e to the negative x squared dx. And then I'm going to think about, maybe I should use u sub. So your A-B integration techniques. Now, if I do u sub and let u be negative x squared, I'm going to have du be negative 2x dx. And that's going to cancel out with this right here and this right here. So I'm left with a negative, which I'm going to put on the outside. And then I'm going to have e to the u du. Now, because I changed my variable to u, make sure that you change your bounds to be in terms of u. So if I were to plug in 1 here, that's going to be negative 1. And then if I plug in t here, that's just going to be negative t squared. I am going to go ahead and evaluate, take the antiderivative. If I take the antiderivative, that's just going to be e to the u from negative 1 to negative t squared. And that's going to be e to the negative t squared minus e to the negative 1. Now, if I were to think about the limit as t approaches infinity of e to the negative t squared, remember that this is going to be the same thing as 1 over e to the t squared. And if I'm plugging infinity here, this is going to be a very big number. So this is going to converge to 0. So now I have negative 0 minus e to the negative 1. And if I simplify that a little bit, I'm going to have answer that converges to e to the negative 1 or 1 over e. So this one dealt with A-B integration techniques. But whenever we do our little whiteboard activity, you will see that most of the problems that we'll do will involve BC integration techniques. I'll leave number 10. We'll do number 10 in class after the little whiteboard activity, and then that should be good.